thanks to this week's sponsor, GiveWell. GiveWell identifies the charities that save or improve lives the most per dollar. One of the most impactful programs that GiveWell has found is the distribution of long-lasting, insecticide-treated nets for protection against malaria. In Africa, malaria kills about 400,000 people a year and is one of the leading causes of death in children. A meta-analysis on the impact of these nets, highlighted by GiveWell's research, demonstrates the effectiveness of these nets over other treatments. GiveWell then looks for the charities that distribute the nets most effectively. GiveWell combines the findings of the studies, models impact, considers evidence, and studies the rate of malaria in different regions to estimate the impact of a donation. They identified the Against Malaria Foundation to be a particularly high-impact charity, able to distribute the nets for less than $5. And the Against Malaria Foundation has demonstrated the need for more funding. A donation can accomplish amazing things when it's directed to a high-impact charity. And new donors' donations will be matched up to $1,000 when you visit givewell.org/dataskeptic. That's givewell.org/dataskeptic. We'll be discussing advancements in the field of NLP, the research that drives it, and the people that push it forward.
I think sentiment analysis helps to provide some structure to text that often doesn't have any. For example, a survey might come with a rating or a score, but there are a lot of pieces of text that don't have the benefit of that kind of metadata. So sentiment provides this sense of a unifying metric that we can use across different kinds of texts to understand basically the sense, right? How positive or how negative the customer is expressing.
So a lot of these classical statistical techniques, they use something called the bag of words. And it's just sort of like, put all the words into a soup bowl and mix them up. Don't worry about the order. Let's just look at frequency of words or the position of words and just very simple structures like that are easy to parse.
Okay.
And there's one last thing I wanted to get to, just because this is going to come up in some of our episodes coming up quick, is something called Zipf's law. It falls in line with this large corpora discussion. Zipf's law basically describes how often you'll see something. So let me just give you the stats and then we'll back up to the definition. In most corpuses, I'm going to quote the Brown corpus in particular, the most frequent word, guess what it is? What's the most frequent word in a particular English document?
In a particular?
Yeah.
What's the document?
Any document, just a random document, a random website. What's the most common word?
The.
You got it. 7% of the words are the in the Brown corpus. Guess number 2. What comes after the? This is hard.
I don't know. Is it like is?
No, good guess though. It's of, followed by third place, and.
And, oh.
Yeah. Very early primitive search engines, one thing they would do to determine, what page to send you to when you put in a certain keyword was to look for how many times that word appeared on the page. Obviously, no one does exactly that today anymore because that's a very crude system. Do you know how people manipulated it?
How? They would just keep repeating the same word over and over?
Yeah. It was called keyword stuffing. So, if you wanted to be at the top of the page for credit card processing, you would just write credit card processing 10,000 times on your page. And then, maybe your competitor wrote it 10,001 times, and that's how they got into first place or something like that. And so, like I said, the is 7% of the words, is 3.5, and is 2.8. And it kind of trails off in this exponential decline. Basically, Zipf's law states that the frequency of any word in a corpus is inversely proportional to its rank in the frequency table. So the frequency table is just the data ordered, a sort from most frequent to least frequent descending. And if you're on the first row, second row, third row, that's your rank, and inversely proportional to that. So it drops off pretty quick. 4 algorithms.
And what's different between them?
Well, that's a big discussion because I have to explain each of them, but let's just call them different techniques. So the perceptron, for example, is one of the classic elements of a neural network, and it has this sort of linear sum and activation. Naive Bayes, on the other hand, follows Bayes' law very closely, and it's a pretty statistical sort of a method. So they're just different techniques for how you might decide which of the words is the right one to fit.
So the accuracy went up significantly, though. So did they make improvements?
Not to the algorithms, no. Same algorithm, more data.
And that's normal?
Well, it obviously depends on the problem. If you're measuring something very, very simple, then, you don't need that many examples. But for all of the kind of interesting problems that you would even think machine learning are appropriate for, this seems to be a common pattern, Train on more images, you get better image recognition. Train on more chess games, you get better chess players.
So just more means more accuracy.
Yeah.
On average. Are there cases when that's not the case?
Well, for sure. Like, let's say you were going to try and use machine learning on some physics experiment, and the parameters are just like temperature, pressure, displacement, this kind of stuff. Those are obeying some very simple physical law, so they're going to do the same thing every time, plus or minus the natural variance of the system,
The goal of this work was to see whether or not it's possible to learn a text video embedding using narration instead of manually annotated video and description. As a proof of concept, we scrapped YouTube videos, especially instructional videos, also downloaded the subtitles that come with them to see whether or not it's possible to learn an embedding from the video and the text part using these narrations. And so the idea of using instructional video is that when you look at instruction videos, when people talk, they are mainly talking about what they are doing in the video, right? Mm-hmm. There is a correlation between what they are saying and what you see on the video, which is great because it's a way you can actually leverage natural language as a way of supervision for the video part. That's briefly like an abstract of what we did on the paper. The idea of the work was not about proposing new model, new neural network, but it's just a proof of concept that shows that, hey, it's possible from narration to learn an embedding. So this is quite agnostic from the model you use. We should not really focus on the model part, but more on the data part, because this paper is mostly data-driven than model-driven. Drawback of this dataset is that it's not as clean as a manually annotated dataset. So, okay, you might have some example where you have someone is saying what he's doing, but he will do it like later or he's doing before. So that might happen. Mm-hmm. So that's not a problem because if you consider a large window, so if you consider a large window for the video might include actually the action. So that depends on how you process the data. For me, that's not a problem. The problems come with sometimes when people talk about something very conceptual. So sometimes they might just say something that's not really correlated with what you see on the video. And that's, for me, much more problematic than the asynchronous aspect of instructional videos. The code, the models, and everything is publicly online on my GitHub. So theoretically, you could actually reproduce the results.
And the common practice is to do crowdsourcing. Frameworks like Amazon Mechanical Turk, and there are probably other frameworks. This is like the famous one. The common practice is to go for some crowdsourcing framework and to recruit crowd workers. And you basically guide them to write the type of questions you are interested in.
Exactly. We had an R&D push, if you will, to try to reach human performance on a benchmark speech recognition task. And we worked on that for about 2 years. And I think we kind of declared success because we did reach a certain human level performance of word level accuracy in transcribing conversational speech.
Usually, researchers do not publish this kind of data. Usually you just have the examples. This is the interesting part. It's all anonymized, of course. You don't really have, the names of the people who wrote the examples, just have some IDs. But when you look at this information, this is where things become interesting because you can see that the annotator distribution or the contribution, like you called it, it's super skewed. The common practice is to just recruit this small group of workers, but it's not just that you have a small number of people who write the examples. It's also like you have these, 5 to 10 people who write thousands of examples. And this is where the concern starts to come in.
Immediately, as a scientist, you have to ask yourself, well, are there qualitative differences in how humans and machines perform? In other words, do we make different types of errors when we try to transcribe speech as opposed to machines? I should also point out that there was a sort of companion task to the switchboard task, which is called Call Home. It's a different corpus where they had people talk over telephone again, but they were people who knew each other, so friends and family who had prior acquaintance, and they were not asked to talk about a particular subject. They just talked about whatever occurred in their daily lives. And that on that task, the computer still was trailing behind human performance. Not by a huge amount, but there was definitely a difference there. So that tells you that the constraints that you put on a speech recognition task really are critical in determining levels of accuracy. And humans are just very much the champions when it comes to flexibility and adaptability to whatever task comes their way.
I expect most listeners will remember that language wasn't always something computers were good at. There was a time when a computer's ability to do anything at all with language was laughable at best.
And at that time, most of the state of the art in machine translation was a rule-based approach where you would hire a team of linguists and language experts to manually handcraft bilingual dictionaries and transformation rules that account for the reordering that occur across languages and other things like morphology and so on. And so it was quite a labor-intensive approach. Around that time, an idea that had been introduced earlier called statistical machine translation was repopularized.
Because simultaneous interpretation is extremely difficult for human beings mentally, it is extremely challenging to kind of concurrently comprehend one language in headset and also speak in another language. It is reported that only 2,000 or 3,000 qualified simultaneous interpreters can actually do this job worldwide. It's just so difficult that each qualified interpreter can only sustain for about 10 minutes, after which you'd have to switch off and they work in pairs or groups of 3, because each person can only sustain for a very limited amount of time, like 10 minutes.
Which were data-driven approaches that took bilingual sentence-aligned parallel texts and were able to automatically align words in the foreign sentence with words in the English sentence, and then use those as the building blocks to then create a probabilistic model.
So when you have humans transcribe the same speech and then do the same kind of error rate computation, you end up with error rates right around 5%. That's again measured against the reference transcription, which was obtained with multiple transcription passes and very high levels of quality checking.
Our technology is not intended to totally replace the human interpreters. We try to reduce their burdens because, as I said, there are only 2,000 or 3,000 qualified simultaneous interpreters worldwide, and there's a huge demand in simultaneous translation because there are a lot of international conferences, more and more like international summits, and a lot of those conferences wanted to provide simultaneous translation or simultaneous interpretation, but there's just not enough supply.
My very favorite author ever in the whole world is Jane Austen. Jane Austen's novels are all in the public domain. And I thought, oh, look, I can get her novels, the full text of them. They're available via Project Gutenberg. You can get the full text of them. And then this is going to be one of my projects for my portfolio. So that was the first time that I did anything with text mining or natural language processing was part of my portfolio to try to transition into data science. An R package called TidyText. And the purpose of this package was to be a bridge between the ecosystem in R, the Tidyverse suite of packages. So if you've ever heard of ggplot2 for data visualization, or if you ever have used dplyr for data manipulation, that world, it's a bridge between that world and text.
Our project looks at using unsupervised learning to assist in classifying phonemes of endangered languages.
What does it mean for a language to go extinct?
Essentially, I guess the technical definition would be the last living speaker of the language dies, and that assumes they haven't passed down the language to their community. And it's quite prevalent now because mainly due to forces such as globalization, which reduce the necessity for knowing these niche languages in different parts of the world.
First, we have, of course, those that have 5, 10 speakers. Even there are only older people that still use that language. But there are another kind of languages that are mostly spoken by small communities, maybe 40,000 to 100,000. Those communities have the problem that they don't use their languages in, let's say, social media or online. So that will be difficult for data mining or other techniques to get all the information and get data sets to work with.
When we define a language as under-resourced languages or language or a low-resource language, there are several factors to it. To begin with, if we are doing natural language processing research, we have to have data. We have to have the corpora for the language. So We need to find all the resources for research and implementation. If a language does not have much written records online or offline, we do not have the corpora to begin with. Speech corpora specifically suffers for that insufficiency.
One of the things that I'm actually quite excited about is the applications of deep learning and machine learning in general for under-resourced languages. Take, for example, languages such as Tigrinya or Amharic that are based in Ge'ez, that are spoken in Ethiopia, where I come from. There's little work to nothing from the big corporations because they don't see the money in it. And one of the things I'm quite passionate about is to follow up this on these kind of languages.
Because I was interested in the written cultures of the ancient world and in the emerging field of digital humanities, which is probably the reason why I referred to what you could call corpora or assemblages of evidence as data sets. We started working together on using machine learning to make tools to aid and extend the scope of an ancient historian's work. And because of my prior interest in inscriptions, we started off with actually an incredibly topical problem, which is the reconstruction, the so-called restoration of ancient Greek texts.
But also from the perspective of the complexity, this language has the most amount of morphemes per word, and it can really do really strange things. We have close to no success doing the machine translation for that language. For example, compared to Nahuatl, that we got comparably good results. So yeah, I mean, there are so many other languages out. So I mostly only worked with 5 of them.
So the task of authorship attribution is you're given a set of authors and you're given a set of texts. What you have to do then is, given a specific text, you have to figure out who wrote that document from that pool of authors that you have. Also, for trying to figure out who wrote certain historical documents and maybe who wrote certain pieces of literature many, many years ago.
When you talk about authorship attribution, it's actually, there are different approaches to this. It's a text classification task, but it can be done supervised or unsupervised. In the supervised setting, you are given a bunch of label texts with their authors as the labels. And what you are trying to learn is a mapping from a text and an author, right? That's the supervised setting. And in the unsupervised setting, what you are trying to learn is a clustering algorithm with its learned parameters that could help you characterize the writing style of a particular author.
Different authors use punctuation differently, for example. And so that's an easy way to figure out, oh, that's Charles Dickens, because he usually puts a comma in between his noun and verb, which was fairly common back in those days, the use of punctuation to denote pauses, as opposed to nowadays, it's a lot more rule-based.
How does this individual organize a narrative? How does he or she lay out a narrative? How does he talk about things? And how does the person reason about topics?
So these are a lot of the stylometric cues that people have often looked at and what we refer to as surface level cues.
Got it. And what are we missing by only looking at the surface level cues?
Discourse, of course. How does an author develop their story? Is that something you would think it would be common across different pieces of text that the same author writes?
For machine translation, our datasets can be as small as 5,000 phrases up to 50,000 phrases. So this is really low resource settings. For morphology, that is a test that is widely used, we have datasets of about 1,000 words, including, we still have to do the splitting in test development and training. So actually we're training with maybe 500 instances, or even less, maybe even 100 instances.
I came up with a fun way to teach this game. Here's how it works. I am going to read a couple of excerpts from the 1983 cinematic masterpiece War Games, and I'm going to ask you to guess what the missing word is. Do you understand the rules?
Oh, goodness. Okay, let's try.
So the first one, I'm going to say blank where there's a blank, and you have to guess what word fits in the blank.
Okay,
You got it?
I'm trying.
All right. Nature just gave blank and started again.
Gave out. Maybe it just gives out. Surrenders.
Close. Okay. Yeah, so the actual phrase is give up.
Oh.
Nature just gave up and started again. But nature just gave out and started again is kind of like that is pleasing to the ear. I'm not going to say it's better, but it fits. And in this context, then, we might learn that up and out are kind of similar words.
Okay. Yeah, I can see that.
That's a great jumping off point is word2vec. And when we started the project, as you probably discussed previously, word2vec is a method for representing input text in a way that we can run machine learning algorithms on it. And in particular, it assigns each word a unique vector. But this is independent of the context. And so in particular, in the word2vec setting, a word like bank or play, these are English words that have many different word senses, and the sense of the word is dependent on the context. In one case, I might be talking about the financial institution, a bank, or in another case, I might be talking about the area of land next to a river. You can't tell which meaning of bank you're referring to until you have, say, the entire sentence or paragraph in which the word is used.
The key thing that's missing there is context.
Context. Yeah, that's a good word. I love it. Yes, context is missing.
The same thing or not. The overall architecture has 3 components. So we have the representation component. That is how should we represent our input? And then the sentence representation learning. How can we learn what the actual sentence means? And finally, a matching function that takes these 2 sentence representations and says, yes, they do match, or no, they do not match.
Having a fast model that you could experiment and optimize is very important. So in the actual experiment, I've seen people reporting that LSTM performs the best, right? So that was the first thing we tried. It did. Indeed, it worked. Well, in absolute performance, it worked better than CNN. But there's a problem with the particular task we're working on, which is we're reading very long texts. We're talking about thousands of words. Because of the sort of parallelability limitation for LSTMs, it's very hard to run a fast sort of experimental cycle, and it's also slow in inference time. If you are doing sequence to sequence translation, that might not be a huge problem with LSTMs. Usually it would do better than CNN, but it was a problem for us. So we settled with CNN.
It doesn't necessarily behave exactly like human memory, but definitely it's memory.
So why do you call it an internal state? What if it's external, like an external hard drive?
Good question. It's less about where we store it exactly, and it's more about the machine learning process. So in machine learning, we have the input, which would be maybe the English text, and the output, which is the Russian text we're hoping to get back if we had, some like good examples that we could train it on. And inside of the machine learning algorithm, it has not just the features of the input, but it can come up with this internal representation, like in its own memory. So maybe, when it sees a certain combination of words, it sets the values in these states to certain numbers. It's just a numeric representation. And it has no real meaning to English speakers or Russian speakers. It's just specific to the algorithm. And for that reason, we call it internal, because it's just inside that algorithm. Or inside the model, I should say.
Okay.
The problem of short text matching, it can be stated as follows. Given a pair of sentences, a model tries to see if they mean the same thing or not. Here's an example. A pair could be something like how to place an order. This would be one sentence, and another sentence could be how do I place an order. These 2 sentences mean the same thing.
My short answer to that is there's definitely tons of noise. That is exactly what I suppose like machine learning will help us out with, is to kind of find the patterns, even though that there's a lot of noise in the data. Generally speaking, don't really clean up the comments so much and just kind of leave them as they are, with the general idea there's so much data that you're still able to learn patterns over the entire corpus.
And then I tried to see how CNNs and recurrent neural networks worked on this separately. And my intuition is that CNNs and LSTMs or BiLSTMs do capture different aspects of the sentence representations. My intuition was for the CNNs, they were looking for n-grams, this term n-grams. If we took, for instance, a CNN of size 2, it would be looking at bigrams, or 3 for trigrams, and so on. Whereas the LSTM was looking for small and longer range patterns in the sequence. And for the bidirectional, I assume before inferring what a given term means, it would look both the terms that came before it and the terms that went after it.
This seems like a rather small corpus of labeled data to work with. Would you agree? Is this kind of on the smaller side of what might be ideal for building a really industrial scale system?
It's true. I would say for current deep learning models, more training data would be better, but it's also very challenging, especially if it is human annotated data.
Transfer learning has quite a long history, and in the past, people have used the term transfer learning to refer to different things. In general, when people talk about transfer learning, what they mean is that in contrast to kind of the classic machine learning, where you have some training data where you can train your model on, and then you typically try to evaluate it on the data that comes from the same task or distribution. Transfer learning, you really try to leverage data or some sort of information knowledge that comes from different tasks or different domains. So typically you have some pre-training tasks or some related data sources that you want to leverage to do better on the task you actually care about.
And so this was the initial intuition for Elmo, is that, well, let's learn really high quality word vectors, similar to Word2Vec, and in a similar manner from lots and lots of unlabeled data. But let's do it in a way that's context dependent, where in the end, when I want to compute a word vector for the word bank, I don't just use the fact that it's bank, but I use the entire sentence or paragraph in which the word appears in order to say, oh, okay, I actually really mean this particular meaning, this particular sense of this word. The pre-trained models, we have them available in a couple of different places. They're available. We have open source code via Allen NLP, which is a open source library that we developed here at AI2. And this is written in PyTorch. So if you're using PyTorch for your deep learning infrastructure now, then this would be a good choice.
That's a BERT, just like the name, which stands for Bidirectional Encoder Representation from Transformers. So I guess it's actually BERFT, but they went with BERT. So BERT is a neural network that takes as input any arbitrary length of text. So it could be one sentence, could be a paragraph. That's really nice because text doesn't fit into a form very well, right? It's not like every sentence is a certain number of characters. Now you have that on Twitter, right, where there's an upper limit, but in general, text is of arbitrary length, and machine learning is not good at handling arbitrarily long things in general. So BERT is built on kind of a sequential model, but what's nice about it is its output is a fixed length vector.
I remember you brought it up in the show, but you know what? Remind me.
So depending on which version of it you choose, you get like either 768 or 128 length of a vector, which is just some numeric representation of that text. And the very surprising thing, or somewhat surprising thing, is that those numbers, which don't have any obvious meaning, are a really good way to do automated feature engineering. So they kind of prepare the text into a numeric format so that then traditional machine learning techniques can learn it very quickly.
And every kind of training trick, be it data or hyperparameters or training for more iterations, stuff like that, we also applied to the BERT baseline. So we had baselines that were actually much, much stronger than the original BERT, and we were still able to outperform them when we added the span BERT objectives and pre-training tasks.
Now there's quite a growing body of research that is concerned with us solving data sets and not solving tasks. So the idea that your training data and your testing data come from the same distribution can be the fact that there are artifacts in the data set from the collection process, from the annotation process, that provide some statistics that models have shown a tendency to latch onto. And they can increase their test set performance by latching onto these statistics that are not what you want to learn and don't relate to the task, but then they appear to be doing really well.
Well, 5 or 10 years has been kind of a magic time period in NLP.
Yes, it has.
How much of that did you anticipate when you started this journey?
I don't know that I could have anticipated it when I started. I was really just getting my sea legs and getting a sense of what was happening.
It's definitely been very exciting to see what is happening with the rise of deep learning, with the rise of models like BERT that make use of pre-training and that have very impressive performance across a wide range of tasks. But what's also exciting for people who, like myself, are interested in better understanding how these models work is the challenge of taking black box, very complex models like these and trying to find ways to illuminate what's going on inside of them, and also to find effective ways of assessing how good they really are at what we might think of as language understanding.
There is one popular argument due to people like Yann LeCun, which could be described as an argument from engineering success. And hopefully I'm not going to present a straw man of this argument. Since we've been using deep learning and our approach has been to try and learn as much as possible and to put in as little as possible either prior knowledge or inductive biases, Yann LeCun famously said inductive bias is a necessary evil, although I'm still not convinced of why it's an evil. But it is true that in doing so, we have seen better and better performance on our in-distribution test sets, which is to say the test sets that come from the same distribution as the training set.
There are certainly, I think some of the most striking results that people have shown tend to be those where they test with adversarial inputs that show that BERT is not able to respond as effectively to those types of inputs, or show that despite the fact that BERT is performing quite well on the benchmark on its face, if you show how the model is really solving that problem, it ends up being that it's exploiting cues in the benchmark that allow it to perform well without really necessarily needing the types of information that the benchmark is designed really to test for. So you have examples, for instance, like despite the fact that BERT has performed very well on an entailment benchmark, if you test it on examples that exploit cues that the researchers hypothesized may be what the model is in fact using, they show that they can get the model down to about 0% accuracy.
And even though we don't understand deep learning sufficiently, so the argument goes, these successes are a strong reason to believe that we're going in the right direction, that the right direction is to put as little prior knowledge into our models as possible, to learn as much as possible from the data, or as someone put it to me the other day, if it can be learned, it should be learned.
This season, as we've been covering NLP, much of my episodes have been sort of a love letter to deep learning and how much of an impact, a positive impact it's had in NLP. Are you able to benefit from using deep learning in your research?
Definitely.
It seems like an easy task to a human. Where does this leave you in your perception of how advanced or on the path towards AGI something like BERT is?
Yeah, absolutely. I think that it's an important sanity check, and it's a useful type of thing to be able to identify because of the fact that BERT does perform so spectacularly well on so many benchmarks, sometimes with superhuman performance. It leads us to really need to wonder, how good is this model really? If we can't find limitations to the model, has it really solved natural language processing? Has it really reached superhuman level language understanding? I think that most researchers are fairly clear on the fact that this is not the case and that this is a limitation in our benchmarks, but it's very useful to be able to identify a very basic limitation like this.
When you first start to learn about neural networks, it's hard to really know what they can and what they cannot do, just for the reason you mentioned. So I know some people that would, for example, hold the belief that train BERT on lots and lots of naturally occurring text and it will learn world knowledge. I've heard people make that claim, even make it last week at ACL. I don't hold that view, but I think it's still interesting to try and apply these cutting-edge techniques to problems, even if they seem unlikely to succeed, just to see how they do.
Sense that a language model might struggle with picking up on a meaning like that. So being able to find a limitation like this and one that we can explain fairly straightforwardly, given the way that these models work, kind of helps us to ground ourselves and is the beginning, I hope, of many more clarifications that we'll be able to find in terms of the linguistic capacities that these models really have. In tandem, of course, people are working on examining the benchmarks that we have, identifying which cues BERT is exploiting and which things it really is.
The distinction that we're making there is that in this paper, we cast every text problem, so every natural language processing problem, as a text-to-text problem. And what I mean by that is that whether you're doing text classification, sentiment analysis, textual entailment, or whether you're doing machine translation, translating from French to English, or if you're doing summarization, whatever, we cast the problem as a text-to-text problem.
The power of deep learning has really enabled us to now build so much better predictive models when it comes to areas like images and video. So it's unlocked a lot, but on the other hand, it hasn't overtaken everything. One of the things I often teach folks to do is we often start with a very simple model, then go to a more complex model. In the cases of areas like images and videos, the simple models just don't work that well compared to the more complex deep learning models.
So Baby is it's a reasoning task. It's actually 20 different reasoning tasks. It was created by Facebook as a part of an effort to understand what would be required as a prerequisite for reasoning in language. So it consists of tasks like, let's say, John went to the kitchen, John picked up the milk, John went to the garden, and then a question which might be where is the milk, or where did he pick up the milk, or something like that. The way we encode this into a graph is we treat each sentence as a node in the graph, and then it's just a fully connected graph. Yeah, and when we evaluate it on Baby, we find that we only need a couple of steps reasoning, but more than one helps. And we get really good results, like we complete all the tasks, and you'll find many papers nowadays you'll find many papers that complete all the tasks. But what you usually do is you evaluate your network 15 times, so you train 15 different networks, and then you pick the best one.
So ONNX is a common standard format for machine learning models. It was actually developed by a number of companies in the industry, including Microsoft, Facebook, Amazon, NVIDIA, Intel, a whole host of companies that put together this standard format for representing deep learning and machine learning models. So you can train your machine learning model in TensorFlow or PyTorch or scikit-learn or MXNet or Keras, and you can export or convert those into the ONNX format. And that kind of gives you interoperability and portability of your machine learning model.
Hi, I'm Lucy Park. I work as a machine learning scientist at Naver Corporation. CoNLP aims to be similar to NLTK for the Korean language.
I think we're talking about the serverless machine learning pipeline that we built for the chatbot that we're working on, right? And it all began with the excitement over the BERT language model, because it could just generate these great feature vectors automatically. The BERT language model could generate these 6-length vectors that had a lot of great features just embedded inside of them. And it was kind of like domain agnostic to these vectors. Like, it was really exciting to think about possibilities because it could handle so many different kinds of text.
The kinds of games that people enjoy playing are just way too complicated for machines. So we've really tailored it so that it's possibly achievable for machines to solve. But that being said, I mean, people were playing it at NeurIPS, and I think those who were not used to the text-based game environment found it challenging.
But based on that, you can actually define the boundaries of the different Spanish dialects. And so we find in particular that there is one dialect that basically corresponds to the area in South America that is more or less south of Brazil. Another dialect is more or less the northern part of Brazil, like where Venezuela, Colombia are. And another one would be more like Central America, so Mexico, Guatemala.